So, as I was just introduced, I'm Dean Saridakis. I'm a software engineer at BAE Systems in Manassas, Virginia. So I'm going to be talking about the RAD55xx platform system on a chip today. So we're shifting gears to hardware now after just countless hours of software. But I have reused things here, so I want to thank Rich Berger and Joe Marshall. They did a lot of these charts and saved me a lot of time. I, as usual, did as little work as possible to put this together. Oh, there we go. Left is down. Okay. So the agenda here, sorry. I'm going to do an overview of the RAD55xx. Oh, okay, thanks. And then I'm going to get into some of the personalities, different instances of this device. And kind of throughout the presentation, I try to draw parallels back to the RAD750, which is kind of our cornerstone product today, and hopefully folks in the audience are familiar with it. After that, the RAD5545 single board computer is our first board design that uses this device. So I'll take a look at that. And just to put things in perspective, I'm not sure how much the audience is familiar with Space VPX and Serial Rapid I/O, but those are some emerging standards in the space community. This device very much targets those systems and those standards. So again, that's really just for context. And while my main purpose here is to get the word out about RAD55xx, I'm also here to get some feedback from the community in terms of software priorities, how you think you might want to be using this, not necessarily during the presentation, but offline or even after the fact. Feel free to contact me with your thoughts on that. Left. Okay, so the message on this first chart is there is a lot of function on this device. It's a system on a chip. That's kind of obvious in the terrestrial world where there's been SoC devices for many years, but in the radiation-hardened world, that's not the norm today in flight. So in the middle of this diagram is the middle of this chart is a block diagram of the RAD55xx, and there'll be a bigger version of that later, and we can look at it in a little more detail. But the message here is in the top left-hand corner is a picture of a current era RAD750 single board computer. And there's 4 copies of that picture because this is a quad core device. On that single board computer, the green arrows are to the RAD750 device and the L2 cache, which is actually a separate device. So in the RAD55xx, all 4 processor cores have both level 1 and level 2 caches in them. The other arrow coming off that board is from the bridge chip, which again in current technology is a separate device. Much of the function in our current RAD750 bridge chip is brought into the RAD55xx. And the bottom left-hand corner is a picture of a SpaceWire ASIC. So there's a few folks here that have used the LRO SBC. It's a few years old at this point, but it was used on several missions. That single board computer had this device on it to get 4 SpaceWire ports. The RAD55xx has 16 SpaceWire ports on it. And there's a whole bunch of other things decorating the graphic in the middle, and I'm not going to narrate those now. We can take a closer look at those in a few slides later. So one thing I want to clarify now is some of the terminology. Apple always sticks a little I at the beginning of the name of all their products. BAE Systems seems to like sticking RAD in the front of anything that's space electronics here. So RAD55xx is for this family of products, and the XX is a wild card. And in the middle, there's a graphics of the RAD55xx die. So there's a single die that comes off the fab. And so going around the horn from the top left-hand corner, there's different ways of scaling the usage of the device to hit your, how much power, how much swap do you have, but how much performance do you need out of it? So in the simplest case, the RAD5510 at the top left-hand corner is a single core version. And it has limited I/O. As you come down below that, RAD5515 takes that single core processor and adds high-speed serial rapid I/O to it. Coming around to the bottom right is the RAD5545, and this is kind of our sweet spot. This is what we're starting with for the first article that we're testing. So that's a quad core, and it's got most of the I/O in the system. The one thing that it doesn't have in it is in the top right-hand corner. There's a bridge to our RAD speed digital signal processor chips. So hopefully the terminology is clear now, and it won't be too muddled. RAD55xx is the whole thing, the whole family, and then there's these different instances of devices in the architecture. So I stole this timeline graphic off of Wikipedia, and it kind of helped me put things in perspective. Hopefully it will for the audience as well. We started with power architecture way back in the IBM days. The RAD6000 was based on IBM's first single chip RISC design, and we took that and did a radiation hardened version of it. Then IBM, Apple, Motorola all got together, created the PowerPC consortium, and based out of that, we leveraged the IBM PowerPC 750 to do the RAD 750 design. And then a whole lot of time passed by, and a lot of evolution in PowerPC. At some point, they renamed things to Power ISA, and we get to the modern day RAD55xx platform. The processor core is called the RAD5500. So I think that's our last instance of, the XX. So it's the RAD5500. That 5500 comes from the commercial design, which is an E5500. So this IP is licensed from what was Freescale, is now NXP, and I'll probably slip up which name I call them. And as with the RAD6000, RAD750, it's identical to the commercial design. So all of the compiler tools, any operating system architecture support that exists for the commercial design will also support this design. This chart's just kind of a little inventory of some of the documentation. I'm not going to linger on it too much. The one message here is in all cases, there's an architecture spec, instruction set architecture, and then for the instance of the design within that architecture, the RAD 750 or the E5500, there's further detail on what's in that design. Again, the commercial documents all apply to the radiation hardened version, and then all the tools and OSs and that kind of thing convey. Then there's a list here for platform level documentation. So that's all the peripheral logic that's outside of the processor core. And there's quite a bit of peripheral logic in this device. The first thing that's listed here is a product brief. There's not a lot of detail in that, but I listed that because you can go get that off the website today. The rest of the documentation is in decent shape, but it's in a draft format. A good backup for those documents are listed here. So there's a platform level document, which is the RAD55xx Core IQ Integrated Multi-Core Processor Reference Manual. It's a mouthful and it's a big document. There's a very similar document from Freescale NXP for the P5020. And there's a lot of overlap in the logic blocks that are in those two devices. So if you're interested in digging into some of the detail, you can go to NXP and get a lot of these documents. There's also something called the Stonewall Complex Reference Manual. That documents the IP that's heritage BAE IP that we've put in the device. Freescale has a separate document for their DPAA, data path acceleration architecture. And for our RAD55xx, there's really just a little addendum. It's a handful of tables that you need to know about to program it. And there's actually one more manual that's not on the list that has to do with the security engine. And I think Freescale kept that separate out of concern for export control. But there's a crypto accelerator in this device. It supports lots of different encryption algorithms that's documented in a separate book. So now we're back to the big block diagram, full size. First thing I want to point out is in the bottom left, the color coding. In the bottom left and the top right, there's a kind of purpley looking blocks. That's all the heritage BAE systems IP. And not necessarily BAE systems. Some of it, like the SpaceWire router, was from Goddard out of the Space Act agreement sharing there. But heritage in terms of what we've used in some of our previous products. Everything else, all the other colors on this chart will map exactly to what you see in the Freescale NXP Core IQ architecture. So that's IP that we licensed and built into this device. And I think I'm going to try to dwell on this chart a little bit because this is always my starting point for trying to understand what's on the chip. And then probably fast forward as we get into some of the detail below. So center on the top are the processor cores. So RAD5500, it's a 64-bit core. Each instance has both L1 and L2 cache. Going to the right from there are the L3 caches that sit in front of the DDR memory controllers. In the documentation, you'll also see the L3 cache referred to as platform cache. And so below that is this big, long blue block that runs across the middle. That is the crossbar switch, the high throughput switch that glues the entire system together. It's called CoreNet, or the CoreNet Coherency Fabric. It implements a lot of the cache coherency protocols that are defined in PowerPC or Power Architecture. And then within that block, you see these little blocks called PAMUs. And the name of it there, Peripheral Access Management Unit, is on the slide. A more industry standard term for that function is IOMMU. So the analogy is within a processor, you've got an MMU that gives you protection and address translation. Well, these PAMUs give you that same function for DMA masters in the system. So you can use these PAMUs to prevent a DMA controller from stomping on some random area memory because you set it up wrong. It can do address translation for you. It has a lot of function. It has this nifty ability such that you can create domains within your system and actually partition hardware so that you have these walls between different domains in the system. So there's quite a bit of functionality there. I have 25 minutes. I could go on for like hours on this. I'll try not to. So going across the bottom, where's the pointer on here? Top. I'll skip the pointer. Going across the bottom, there's this boring white block that says 24-lane SerDes. So there are 24 lanes of high-speed serial I/O. They can run anywhere from 1.25 to 5 gigahertz. And there's different protocols that can be multiplexed over these depending on your application. So the blocks that tie into that on the left is serial rapid I/O. Going over towards the right is gigabit Ethernet. If you're familiar with SIGME, it's 1.25 gig to get you your effective 1 gig rate. And then on the very far right, there's something called Aurora, which is a another protocol. A lot of FPGAs have that protocol in it. And in this case, it's used to do streaming out, high-speed streaming out of debug information. So there's debug trace capability built into the device. I wouldn't expect that to ever be used on orbit, but in a lab integration environment, if you can go back and stream out big chunks of data about what's going on in the system, that's a really helpful debug tool. That's in addition to sort of the legacy heritage JTAG COP interface, if you're familiar with that. And then, so sitting in between those blocks are what's part of this DPAA function in the system. So continuing with the rest of the Freescale IP, over here on the left, there's a whole stack of other oddball, I won't call oddball, other functions in the system. Some of the more significant ones to point out, there's a NAND flash controller. There's an I2C controller. That's important because I2C is part of the Space VPX standard. There's power management. So again, I said even though it's a 5545, you can run in a scaled down mode with using the power management function. And security monitor and internal boot ROM are part of what's called the trust architecture. I have a chart on that later that we probably don't have time to look at too closely. And again, down here in the bottom left-hand corner is some of the legacy function from RAD750 era devices. There's 16 ports of space wire coming off the device. There's a 32-bit PCI bus, SRAM and EEPROM controller for legacy devices. And then finally the Clear Connect bus to the RADSpeed DSPs on top. So this chart kind of goes into some details on the RAD5500 core and does a little comparison against the RAD750. The first most obvious difference is it's a 64-bit core. It can run in 32-bit mode as well. Of course, you can switch back and forth. Excuse me. In general, it's evolved over the past 10, 15 years, however long it's been. So it's a higher performance processor core, and some of the stats are listed at comparison on the right-hand side there. So more floating point and integer operations. It's a 64-byte cache line versus 32. The physical addressing is 36 bits, so you can get up to 64 gig of physical address space. And then all the arrays on the device are protected by ECC. So all the level 1 and level 2 cache is protected by, is ECC protected. The only thing on this features list I want to point out is the IEEE 754 floating point. That's compatible with the floating point in the RAD750. There was a time and some devices in between. There was an alternate floating point implementation, some kind of embedded floating point. I'm not very familiar with it, but this is sort of the floating point classic, if you will. The other big difference is multi-core. So that's the big change over the past 10 years or so. And all the function that's built into the core for that, including the cache coherency support, full MESI coherency. Cache lines can be locked on a line-by-line basis versus the entire cache. And there's an embedded hypervisor capability as well. So in addition to having supervisor and user modes, there's a guest mode. And how are we doing on time? I'm just going to do a quick paraphrase of these next couple of charts. And the reason these are in here is if you look at all the piece part components on that big block diagram, you might miss some of the architectural intent of the design. So one of the things is this data path acceleration architecture. and it's a way to offload a lot of the I/O movement in the system. Both this chart and the next chart, if you're interested in getting more detail, NXP has some great educational outreach material on their website. And so I think there's like an hour-long presentation on both this topic and the next topic. And obviously they'll do a way better job than I would here in a couple of minutes, so I'd point you to that. So at any rate, just real briefly, there's a buffer manager, a queue manager that sort of sits in the middle to facilitate this acceleration. There's your actual I/O interfaces, so FMAN is the Ethernet frame manager. RMAN is the rapid I/O message manager, and there's several instances of that block in the system. And then SEC is the security engine that does the cryptographic acceleration. And this chart talks about the trust architecture, and there's a few different elements to this. One is a concept of secure boot, which may or may not be a big priority in the space world, but the F6 program was very interested in this, and this design met all of their requirements. So that's a way to securely boot and check that your system is running what you want it to run. There's the couple of other things I pointed out earlier with the hypervisor support and the processor, and being able to partition and have safety in that sense, and then the PAMUs with the I/O, MMU, that kind of control. So this trust architecture is all the things that are implemented in the hardware that are trying to facilitate deploying a safe, secure application. This is a block diagram customized for the 5545. I'm not going to dwell on it. I will point out one kind of error on here is on the bottom right-hand corner, the frame manager is ghosted out in this picture. But the frame manager, which provides Ethernet, really is available. And so I just wanted to have this as a segue into looking at a block diagram of the 5545 SBC. So let me first just back up to a couple things I should have mentioned earlier. The RAD55xx silicon is a 45 nanometer radiation hardened technology, and we got first silicon in the middle of 2016. So this SBC is our first board design that uses that device, and that's in or just out of manufacturing as we speak. If I was back home, I might be getting yelled at to go down to the lab, I'm not sure. So at any rate, this is our first design that uses the chip. It is a space VPX single board computer. So going along the bottom of the block diagram are the various space VPX backplane interfaces, the utility plane, and the other I/O into this utility FPGA, or the low-speed I/Os. All the high-speed I/Os go directly to the RAD5545 in this case, so there are 3 or 4 rapid I/O links or ports, and each one of those can have 4 lanes of traffic. There's 12 of the 16 SpaceWire ports are routed to the backplane. So the other thing with this card design is it's pretty flexible and modular. So for instance, the DDR3 memory is on a connector. So you can put in a commercial DDR XR-DIMM, or you can go to a more rugged space qualified DDR device to plug on here. And of course, the amount of memory you get can vary based on what you put on there. It has a mezzanine connector to put a daughter board on there, and run to that mezzanine are the interfaces you see there, PCI for the SpaceWire ports, and potentially a rapid I/O. at any one point in time, you can only use 4 rapid I/O ports, so you sort of have a decision of, do you want all 4 to the backplane, or 3 to the backplane, and 1 to the mezzanine? But it's got the flexibility. You can run it either way you want. And I guess the last thing to mention on here is on the upper left, we have NAND flash, which is in a TMR, triplicated configuration. And the reason that is attached directly to the utility FPGA is the NAND controller is in the 5545, but the TMR function is implemented in the FPGA. So that's what does the voting, reads and writes all three devices, and does the correction. And this is a word chart for the previous picture. Let's see if there's anything important I missed on here. I'm going to say no and move on. So again, this is a real whirlwind. What the heck's Space VPX? So Space VPX is defined by VITA 78. It's an open standard, and it was based on previous VITA standards. So based on the VPX and Open VPX standards, and a couple of the main goals, deviations from the existing standards that says, well, why does this have to be different for space, was fault tolerance on the utility plane. So previously there was a single point of failure there. They designed that out of the system. And then adding SpaceWire, which really isn't used in terrestrial VPX systems. So they define a bunch of different module profiles, and like a lot of standards, there's a lot of flexibility to it. I won't attempt to get into those profiles. But this is just notionally a VPX backplane with a bunch of modules on it. And on the bottom, you can see there's a data plane with rapid I/O for your very high-speed I/O in the system, SpaceWire for control plane. And SpaceWire isn't too bad for moving data around, so depending on your data rates, that may be applicable. I2C is used as a utility plane, so you can see this little module on the left is the utility manager. So it can do health checking on the various modules in the system, potentially turn things off and on, that type of thing. And then there's room for expansion. There's expansion planes. In this diagram, it's marked as ZOWI. It could be ZOWI, it could be anything else. In fact, we have a RAD55xx Space VPX module now. Now, in that particular design, it's parallel PCI that's brought out to the expansion plane. And I'll just briefly say there's several instances of the RAD55xx in different applications on this device. And there's a bunch of other devices that have RAD at the beginning, and they are, I think there's 3 of them on there. 2 of them have been fabbed or been designed into systems that are being integrated right now today. And the 3rd is finishing up design and will go to tape out sometime next year. So there's a whole family of products we're bringing up around the Space VPX architecture. And so my last chart here before I get to the please tell me what you think you want chart is rapid I/O. And so yesterday, listening to Steve from Star Dundee talking about, Parks, thank you, talking about space fiber, a lot of things he was talking about are common and similar to rapid I/O. So if you can take what you heard there and apply it in terms of having SerDes links connecting the nodes and 8B, 10B encoding and these, 1 1/4 to 6 1/4 gigabaud nodes, and packets being transferred with checksums and acknowledgments that you have guaranteed delivery. All those things apply here to serial rapid I/O. There clearly are some other differences. In this case, your lane configuration can be 1, 2, or 4. And on the right-hand side, there's a whole list of transactions that are defined by the rapid I/O standards. So these are transactions that are implemented in hardware. And then this graphic shows just the stack of rapid I/O, and then I put some annotations in here for the various parts of the standard mostly to help me navigate the standard. But part 1 defines the I/O system. That defines maintenance transactions and the nread, nwrite, sread, swrite transactions. Maintenance is what's used for plug-and-play type operation. So think of it as PCI configuration cycles, or what SpaceWire plug-and-play was doing. You've got a configuration space. You can do these accesses to go see what's out in the system. The nread, nwrite type operations are like SpaceWire RMAP, but it's implemented in hardware. So nothing for software to do there other than do a memory access, or maybe a DMA if you want more efficient access across the network. The message passing defines the message and doorbell transactions. So these are more network oriented. There's been a couple of implementations of TCP/IP on top of serial rapid I/O, and those implementations use this message transaction. And then doorbell is just a really, really short message with, I think, just a 16-bit payload, and those are great for interrupt type operations. If you have a peripheral device, have rapid I/O implemented in FPGA with a very small footprint, that's a way for the FPGA to, ship some data out through a memory mapped access and then send a doorbell, say, you've got mail type of thing. And the last thing I'll mention is data streaming, which is on the far right. Those are far larger packets. They don't have guaranteed delivery, but there certainly are a lot of applications where that really is the most appropriate transaction for an application. And I'm definitely not going to read this chart. This was just me kind of throwing up what are all the things I think about about wanting to deploy a system to this RAD55xx architecture. And some of it's coming from RAD750, where I've got this mindset of a single core. My impression is that many applications just run strictly in kernel space and don't do address space partitioning. So this is really just an open invitation, not right now, but later on tonight or tomorrow or through email. If I can get an idea of where you think you're going, what you think your priorities are, that'll help us to prioritize what we're doing back in Manassas. So I think at this point, I don't know if we have time for a question or two.
Question? Okay, as I'm walking with the microphone, tell me, when can I pick one up?
When can you pick one up?
Where's the EMD?
Wow, really soon?
Is it?
Well, so the first board is in fabrication right now. It's on our manufacturing floor. So we'll have it. I'll have one very soon. I don't know when we're going to go to a production mode type of thing. I'm too wishy-washy to commit to anything like that. Sorry.
Hi. Is the Space VPX ITAR?
No, it's defined at Vita 78, I think? So that is not an ITAR specification. No.
Okay, good. Yeah, then I can get one a daughter board. Okay, good, thanks.
Sure.
More questions? Nope. Okay, thank you.
Sure.